So the first page will be our Meetup GNHA page, right? Yes. Welcome to the Recurrent Healthcare Analytics Group, and thank you for coming. Such a good weather, and I really appreciate you not going out, but instead coming in. And thank you very much. My name is Christine Lai, and some of you may know me already, some may not. I'm so sorry to apologize that I didn't come in the last few meetups. Yeah, because I was out of the country. So I'm not back. So I will be more active and helping Chad and May and all the others to get us together. I see that everybody's here. Do you have any questions so far? If not, we start our meetup. How about that? Yeah. And there are food and drink there. Feel free because we have sponsored for that. And just grab anything you like. Okay. And you get your chair. Okay. And if you need anything, let us know. First of all, let me introduce how many of you have come here the first time? Wow, quite a lot, okay? And I'm very excited, yeah. And of course, I welcome back those people that have already been here, and then also welcome to the new members. And first of all, since we have so many people new, let me introduce our group. Greater National Healthcare Analytics is a group for those who are doing or interested in healthcare analytics to share ideas and keep up with changes in our industry. It originated back in late 2012. There's a group of people from VUMC, stand for Vanderbilt University Medical Center, like me, and Med Solutions, HCA, and Tank Care created this group. We've been using Yammer.com back then, and then later we moved to Meetup to communicate with each other. And so all friends, if you have friends that are interested that couldn't come in today, please spread the word. And also thanks to May, we can have the live stream and people can click to our website and click the YouTube link, and then they can hear the video as well as seeing all the PowerPoint. So we are open to anyone, and we are not specific in SAS or any other tools, and any tools that you use, we would like to share and with one another. Okay. To make the long story short, then first of all, let me introduce our speaker today. And I have a long script here. Our speaker today is Aaron Arisomagatula, right? Yeah, and he's am I right?
You're right.
He's correct. Yeah. So he's a data scientist at Pop Healthcare and focusing on advanced analytics and machine learning and artificial intelligence solutions in the Medicare risk adjustment and analytics space. I love that because I never have no clue what the just means. So I will pay attention today. And Aaron has been working in areas of advanced machine learning, deep learning application in both provider and payer settings. Prior to joining Pop Healthcare, Aaron worked as founding member of data science teams at Aspire Healthcare, Tenet Healthcare, and Geisinger Health, and he is devising algorithms to assist accountable care organization, ACOs, and various other departments like emergency services, immunologists, and clinical engineering. He received graduate degrees in experimental particle physics, wow, yeah, and civil engineering operation research. Those I never dare to touch. And from Texas A&M University, College Station, Texas, and has authored in several peer-reviewed journals and conferences. So please welcome Aaron today.
Hi everybody, and welcome here to the first GNHA Meetup lecture or talk for this year. And I thank Christine and Chad and May who invited me here. And They have been actually asking me for a long time. I can gather the, what do you say, enough courage to do that. But finally, I'm here. So let's hope it's a good talk, and I really hope people like it. And if you don't, just don't hit me with that. Any case, so I know I've seen that this talk, just by the nature, how people get into like a lot of keywords and all that. It's like a Facebook for deep learning, and then the talk doesn't have anything about it. No, it's not like that. I assure that there's a sizable amount you're going to learn if you haven't actually already start delving into deep learning or on the space, because it's huge, right? So when we talk about deep learning, it's not really a term, it's like data science. Specifically for the talk, I picked up my idea of this talk, or the structure of this talk, was that I would provide you some basic idea of what deep learning architectures are and how things work for different architectures. At the same time, provide use cases which do not involve video, audio, or pictures, or that kind of thing, right? So the reason for that is that I think today you go and you Google search deep learning, and the very first 100 pages would come with applications on face recognition, audio generation, video generation, text generation, right? So the idea basically was to show that it's not really limited to that. There are all these different use cases, and it's really versatile. The whole field, and it can be used. It's pretty easy actually. Okay. A few pointers before I actually get into the slides. In terms of technology, I picked up R. A lot of people, I assume that in this, who are sitting in this, context, most healthcare people, they're very, accustomed to doing stuff in R, right, and not in Python. That was one of the assumptions. And the second, more exciting thing is that you can actually, so you know what RStudio is, right? It's the IDE you can write R programs in. You can actually use Python-based deep learning frameworks like Keras or TensorFlow. So I think most people who haven't heard about deep learning, they also know about TensorFlow, right? Google's offering in the space. You can access all that heavy machinery just from your RStudio. And you can actually write an R program. You don't even have to learn a new language. That's exciting, right? Okay, so so let's get into the talk. So I would like to stick to the agenda here, basically try to follow a structure. I'm going to start with talking about my company for a little bit, just to tell you what we do and what I do in the company, right? I think it's kind of important. They let me talk here. The second topic I want to get into is just give a small primer on what type, how can you classify? This is one of the classifications. There are multiple, obviously, out there. One of the classifications scheme in which you can put predictive algorithms. So, I'm going to talk more about it in a bit. Then I'm going to introduce some very popular deep learning architectures, very 3 or 4 different architectures, and how they differ and what kind of use cases you can use them for, and we can discuss. And by the way, if you have any questions or if you don't understand something or you want to add something, please do it. I'm all for it. I really like when people try. I'm going to introduce you guys to a few, maybe 3 or 4 different architectures, and literally we cannot do any more than that. There are thousands of architectures out there, and I'm not kidding. It's true. Basically, what happens is that it is a field in which there is a lot of active research going on, and every other day you would find literally hundreds of papers which come out with either they take one particular architecture, very popular architecture, and tweak it a little bit for a problem, or they actually introduce their own architectures. So I don't even, if you ask me if I know the names of, say, 10 architectures which came yesterday, I wouldn't be able to, because it's just proliferating like anything. Okay? Then we'll jump into some case studies. So I'm going to actually talk about some data sets which are public. So by the way, all the case studies here are publicly available data sets, and I have given references and links to all of that. And on top of that, I think I have provided presenters with a GitHub link. So all the code is also available to you by themselves. So you can use it on your own data set, you can play around, and it's all open source. You don't have to buy anything. Okay. So so the very first, so I have a few case studies, and anybody who's interested in NLP here, or who's NLP, yes, natural language processing, NLP, in operational research, also called non-linear programming. We're not getting into that, okay? In any case, so I would try to introduce a paradigm called word embeddings. So the idea basically is that if you have lots and lots of text data, depending on what is the context of the problem you're solving, you can represent the text data into numerical vectors. And you know what you can do if you can represent text into numerical vectors, right? You can use them in regular machine learning algorithms. It's beautiful, actually. It's not something very new. It has already, I think, Word2Vec, which is one of the most popular algorithms, which does word embeddings. It started in 2011. So it's almost 6 years old, 7 years old, right? So we'll talk about that. I have an example for that as well. And then I think I'm going to close, and we'll have time for more questions. Okay, does that sound like a plan? You good? Okay. So, so I work for a company called Pop Healthcare, which has been around since 2010. Okay, it has always been a privately held company. We are basically an industry leader who partners with providers and payers, and we are we have proven solutions for risk adjustment, and also we have started since 2015, 2016 into providing tertiary healthcare to Medicaid members. So the idea basically is that we hire nurse practitioners and physicians who take care on a monthly basis or weekly basis to people who need chronic care at home, so that they don't have to go to their PCP or go to a hospital as often as they usually do, right? So it's a really good plan or program, and then there is a lot of analytics that happens around it. So when we try, for example, it's a plan, it's something you want to sell to people, right? So who do you sell it, right? So there's a lot of marketing that goes on, there's a lot of targeting that goes on, right? We use a lot of predictive analytic models to do that, and then we of course also do a lot of monitoring. And we have tertiary services which help us streamline, our operations, right? So there's a lot of analytics that happens in that. Okay. We right now are in 49 states and Puerto Rico. The only state we are not operating in is, I think, Alaska. And PHC, Pop Healthcare short PHC, is basically we got acquired by Guidewell Group. If you have heard of them. Anybody in healthcare? You guys have heard? So Guidewell is a huge non-profit organization out of Florida. And have you heard of Florida Blue? The Blue Cross Blue Shield of Florida, right? One of the, I think it is the largest managed Medicare population in the United States, right? Guidewell owns them. So we are now a sister company with Florida Blue. Okay? And we also, of course, take care of the Florida Blue population as well. So that's about the company. Okay, so now before we start and we get into deep learning, I just wanted to give a small introduction on how I perceive predictive algorithms. There is no one way of doing it. There are multiple different type of classifications, how different algorithms are. But this is one of them. So you can classify algorithms majorly, predictive algorithms I'm talking about, into 3 types. Okay. So the very first one are structural equations, so or structural algorithms. The idea is very simple. When you try to predict, when you're creating a model to predict, like, you have a target variable y, and you have like a lot of data which you want to predict this variable on, right? This target on, right? We start with an assumption, right? We basically say there are patterns in our data set which are very much correlated to our target variable. If there are no patterns, you would never be able to do any predictions on them, right? It will be chaos. It will be basically, you'd be better off doing a coin toss, right? So the structural equations classification is basically when you assume that there is a direct mathematical equation between your target variable and your predictive variable. Understand that? Like it's very simple. Like when you, let's say that your predictor variables is a vector x, then you're basically saying y equals f of x, right? And one of the examples for that is the most famous algorithm like linear regression. So what you're basically saying in linear regression is that if you take your target variable y, then the target variable is is a linear function of your predictor, and you're trying to find out what that linear function. So the thing is that you're actually assuming even the form of the equation, right? You're basically saying it's a linear equation, and we know that it sometimes helps and it sometimes doesn't, right? Like, because most problems are not linear. So there are other structural equations too. So I'm thinking that if you people have dealt with machine learning, then you have already done enough linear regression and Bayesian regression, right? Here you have actually done quadratic regression. Anyone? Okay. So what is the assumption when we are trying to fit a quadratic model?
Square.
Right. So basically, what you're saying is it's a second order polynomial, right? You're basically saying it's your y is equal to f of x. F of x is basically a quadratic equation, right? And you can imagine it goes on and on. You can have a cubic equation. There are all these like spline methods which people use to fit and all that. And by the way, spline methods are also, they're not typically a machine learning method, but you can imagine they are structural equations. If your assumptions are correct, they are very good at predicting too, right? Under their limitations. Okay. By the way, there are two pictures up there. You can see the one on the top. That's basically the linear regression models. They're assuming that your data and your predicted values they're following a linear trend, right? And then you're trying to figure out what is the slope and intercept and all that. And the same with the quadratic one. Let me know if I'm very monotonous. I can get monotonous. Okay. Then there are other predictive models too. So we have structural equations, which basically we start with an assumption what is going to be the nature of the function, right? Nature of the relationship between those two, predictor and predicted values. We also have tree-based algorithms. So very popular, right? Everybody, I'm assuming that you have worked with relation trees before if you have predictive models. And nowadays nobody does relation trees, right? So people do ensembles, people do random forests, people do XGBoost, right? CatBoost, whatever. So what really tree-based models are doing? So when I say ensemble, basically the idea is that you have one particular type of model. We can, for example, have an ensemble of a linear model as well, right? What it really means is that you basically take you fit 100 linear models and then you take an average, it becomes an ensemble. Okay. So for the tree-based model, the tree-based models basically what they do really is that it's basically trying to fit business rules, right? People work with, you guys have worked with business rules. So usually when you do analytics, let's say you have a data set or something, you want to divide your data set. So you basically say, okay, I'm starting with young customers who buying technology, and then there are older customers who want to buy say something else. I don't want to say guns, but I'm so sorry. that was a bad term. Okay. Anyway, but the idea basically is that you can do that, right? If you have the history of purchases for these guys, right? So when you know the purchase history, like what people are buying and when they're buying, how much they're buying, you can basically cluster them off using certain rules. say that, okay, if somebody buys a certain kind of product more than 30 times a month, and then like how much you buying, all that, you can come up with, you can build them in different buckets, right? That's what we are doing. The only difference here is that you are not creating the rules, right? You are letting the algorithm come up with the rules directly from the data. So that's where the fitting, the training happens, right? So if you open up like a decision tree model, the idea basically is that what you are going to see is you're going to see something like that, right? You're going to see a bunch of nodes where a split happens or a decision happens, and then that decision puts like the data set or the people or the members or whatever into different buckets, right? And the idea basically is that depending on what problem you're trying to solve, the final tree would be the best way to, like, put them into different buckets so that you can identify who's who, right? If you're doing a classification problem, for example. Okay, that's what it is. And I'm not going to get into the details of like how it does, it gets boring, right? But it does it pretty well. We all know. Lots of competitions have been won by random forests and residues and all, right? So there goes your proof, like proof is in the data, right? So now it starts getting interesting. Because I think most of us already knew what I was talking about, like the first classification, the second classification. The third classification is also like the first classification, right? You're basically like it's like structural equations. The only difference here is that we are not even assuming what is the relationship, right? No assumptions. So we're not saying that y is equal to f of x or f of x is something, and then trying to figure out what the coefficients are. We don't even know. We don't care for like most of the time. So so that's basically like the third one. I basically call it a function approximation. And there are multiple things which like are function approximation algorithms. How many of you are engineers? Okay, I know engineers is like a big term, but most of you guys have worked with transforms, right? Like Laplace transforms or Fourier transforms, right? Or Fourier series, by the way. Fourier series is a function approximation way of function. The only difference is that we are doing it analytically. We are not letting the data decide what the coefficients are, right? But there are algorithms which, like apart from right? Which do that too. So, for example, have you heard of Gaussian processes? Anybody? Gaussian processes, right? So note it down if you want to, because these are like really these are some really good algorithms which came before deep learning models, okay? And which are which people still use. I use them like whenever I can. It helps me guide my deep learning algorithms better. Okay? Anyway, so one of the examples is of course Gaussian processes, which basically what we are doing really is that we are guiding our algorithm to not assume the shape or form, but basically start with an approximate value, and then go to as close to the the equation, structural equation as possible given the data. Okay. And another example of function approximation algorithms is of course deep learning. Otherwise, I will not mention it, right? So deep learning algorithms can you can call them function approximation. You can also call them representation learning. Have you guys ever heard of that? Right? So what deep learning models really do is that they try to learn different representations of the same data, and then try to see if those representations are any better at figuring out the final pattern, which makes the decision easier. Okay. Please let me know if any of these words not make sense. Okay, I'm assuming right now that okay, this is all okay. By the way, the picture on the top there, right? It's an analytical function, basically f of x equals x sine x, but it's fit using a Gaussian model. So it's not really exactly that function. As you can see, there are confidence intervals around it. So that is how it looks like when you basically try to sample out using Gaussian process model. Okay, so that's how it fits it. So it starts with certain certain what you say starting values or trial values, and then the model basically learns as it goes, how to fix those. And also there is a lot of stuff which also happens in background and also functions. But that's basically what it does, right? And you can see like how it looks like. So this is an approximation. The blue line here, right, on top here. The blue line is the actual prediction, and the red line, which right now, as you can see, is like pretty much like covered up, is the function, the real function. So because because it's an approximation algorithm, it approximates almost pretty much the same around here, but then the actual function, it deviates from the actual function, it goes away in a different direction. So you can expect that, right? You can always expect that if you're fitting a model, something will have some error. So that's the error in that. The picture below is a deep learning model. It's not scary. I would say that because I've seen scary architectures. There are some architectures which you probably will have to fill the walls with, and it'll still keep going. By the way, do you guys anybody who does not know what a neural network is at all? Anybody? I should have asked this before, but no. Okay. So you guys understand what a neural network is when I throw this picture at you. That's what I'm saying. Okay. Because if we don't know what a neural network is, then I would actually take some time to explain that, and then we can go to the next. By the way, the case studies are much more simpler. You'd actually laugh at me. Okay. So now we are getting into types of deep learning architecture. So you looked at what deep learning was. I basically defined, I said deep learning is nothing but it's a function approximation, right? You're basically thinking, what you're saying is you're assuming the fundamental assumption of machine learning is basically that you have a predictor, you have a target variable, you have predictors, and there is some pattern, there is some correlation between these two which you're trying to learn, right? That is always the assumption. The only difference with deep learning models is that you are not assuming the form of the correlation or the function between those, or function relation between those. Anyways, so some of the major architectures now people have repeatedly talked about, and I'm going to just introduce to you guys in a bit is. So we have AutoEncoders, my favorite kind, right, which are the rock stars right now. So all the buzz is about convolutional neural networks pretty much. And a little bit, I wouldn't just dismiss the other types because they are also catching up, right? We have recurrent neural networks, and then we have a type of recurrent neural network which is a little bit better than what RCNN is, right? The long short-term memory networks. I'm just repeating the names just to see how many of you recognize the names. How many of you actually recognize these names? These are pretty popular ones, right? Right? So you know they're gaining popularity, especially the third and the fourth one, right? The recurrent neural networks and the LSTMs. They are actually much more popular now than CNNs because they have much more, what do you say, applicability in different cases. Okay. And I just mentioned I'm gonna just mention the name generative adversarial networks or GANs, and we're not going to talk about it. Okay. This is a topic for another night, not for today. But just think about it, and if you can read upon it, it's very interesting and also very experimental at this point. The GANs are really experimental. That's why I didn't even want to mention. And literally, thousands more are there. If you want to just read up, it's very difficult to even, I think, put all the different architectures in one page. Okay, so we're going to talk about some of these. So let's start with AutoEncoders. So AutoEncoder is a very, very simple and probably the very first type of deep learning architecture that was there. What an autoencoder is really trying to do is it's how it is a function approximation algorithm, right? Like deep learning a function approximation. So there must be a function. The only deep learning architecture we know what the function is already is autoencoder. So we know which function we are trying to approximate. We are trying to approximate the identity function. Okay? So if you start with a vector and you push the vector through, like you make it take the vector, push it through an autoencoder, the output is supposed to be the same vector, or the same example you started with. So it's supposed to learn itself. Now that's boring, right? Yes.
Your slide says that you're doing back propagation in an unsupervised environment. How are you doing back propagation without labels?
Why did you say that?
The first bullet point, that an autoencoder neural network is an unsupervised learning algorithm that applies back propagation. Am I reading that wrong?
No, you're right.
The input is the label.
It does it, right? It does that.
But that would make it supervised if you have labels. Am I missing what you're trying to say?
No, you're not missing it. It's okay. The whole idea is this. So we do have a target here. We know what is the label, right? When it goes outside, it's the same. Input is equal to output. So there is that backward that's happening. But when you say unsupervised doesn't really mean that. So backpropagation really doesn't mean that it is supervised, that there are labels all the time, right? So here, what you're trying to learn is you're trying to learn a representation which you didn't know. You're not trying to do a supervised task, which is basically trying to figure out if it is a classification problem, or we are trying to equate to a value, right? You understand what I'm saying? So it's not in its classical sense. It's not really unsupervised task, but it is, right? So the final goal is different. When you look at autoencoders, the final goal is not trying to learn a task. In a sense, so usually when you do a machine learning model, it's basically trying to learn a task, right? Autoencoders does not learn a task; it just creates a representation. So that's the big difference, and it does have backpropagation. Okay. So I was saying that in its essence, if you just look at the definition, it's quite boring, right? Autoencoders, because it's trying to learn itself. It's basically what you're doing is you're starting with certain data and you're saying that the algorithm is going to learn the same data back, right? Then what is it really doing? Why is it even useful, right? So it has its use. In fact, it's wonderful in certain areas. Okay. So the very first thing is that how many of you have done clustering or PCA before, right? So anybody can anybody just say what do you do when you do PCA? What happens when you do PCA? You start with data set, you apply an algorithm, right, and it produces another set of another data set, another set of variables, something, right? Yeah, sorry, you were saying.
Principal components.
Yeah, so it produces principal components. That's what we call, right? And what can you do with those principal components?
You can build features for image classification.
Other tasks, right? So basically, you can use whatever is the output of the PCA as inputs for another classification. So what it is really doing is it's compressing your data set or the information in your data set into another data set with lesser features in terms of numbers, right? It's simple. It's supposed to be compressed, right? So it has some error when it does that, and the error basically comes out because you're using. When you do PCA, you start with n features. You actually get n components, but you pick say the top 5 or top 10, whatever in the application, right? So because you don't pick the other components, you lose some information, right? So what it is really doing is it's sort of like taking your data set and it is transforming it. So like your Laplace transform and Fourier transform, right? It's transforming it into another space. But the transformations, that means if you start with a set a data X and then you go and you create like principal components, the direct relationship is linear between the principal components and the input data, right? What AutoEncoders do, you can do the same thing with AutoEncoders, actually. Okay? So you can, in a moment, I'll show you what it is really doing. But you can start with, say, n input values, right? And you can squish that data set by using a hidden layer which is less than n, or number of units in the hidden layer in your, in your network, which is less than the number of input dimensions, right? And then because you're already what you're really trying to do is you're squishing it and then reconstructing the data back. But because of the compression that happened, it learns the representation, right? But again, it is noisy. It's just like your PCA. The difference is that it is non-linear. Understand what I'm saying? So if you're if you do PCA, sometimes what happens with PCA is that the principal components learned are not really that numerated, right? But it really depends on how. So okay, the question pretty much is that we do a lot of analysis, right? When you start training a model or something, you start with your raw features, and then you basically say how many of them are correlated, how many of them are parallel, collinear, and all that kind of stuff, right? And then the problem is that it's not necessary that the features are always linearly correlated. I think I was talking to my wife about this yesterday, right? So, and there are very few methods which can even allow us to look into nonlinear correlation. Okay, so AutoEncoders gives you a glimpse into that. Again, it's like heavily biased towards tuning, how you tune your model and all that. But it does give you a window into real nonlinear correlations. Okay. So it's very useful, and in a moment I'll show you I'll give you an example and you'll see that how you can use an AutoEncoder. But people have used it for multiple applications. They have used it for clustering. They have used it to do PCA-like analysis, right? Basically come up with, and that was actually one of the first applications. So even when they were doing CNNs, right? So you just said a PCA you can use it for another application. So that's what they used to do, right? They basically use an AutoEncoder, compress the image, and then push that AutoEncoder layer as the initial layer, as the input to our CNN, right? So to do image classification.
So have you had a lot of luck in experience compressing features like this with the smaller hidden layer?
No, this is just a what do you say, a toy representation, right? So usually you can go with 2 layers, 3 layers, however it works. And then not all the hidden layers will have the information you want, so you can pick up which exact layer you want, right? Yeah, I mean that is always there. But the idea basically is just to introduce that these things exist, right? People use these methods basically to look further into the data and learn more representations or learn more patterns. So AutoEncoders are very useful. It's not always LSTMs or CNNs and all that, right? Fancy stuff. By the way, one question: if you guys are contemplating, and I specifically said that it is useful because you start with say n layers, and then you reduce. Also, you start with say n inputs, and then you reduce the number of inputs. Right, and your units is lesser dimensional than the input units. Right. What happens if the units are more than? So if I started with a layer, a hidden layer, which has say n plus m units when I started with it. It's kind of interesting, right? So I would highly recommend to just see, start with a toy data set and fit a model and see how the difference. So the idea basically is that it gives you more patterns. You're fitting your data in. You're basically taking a 2-dimensional data and putting it in 3 dimensions, and you suddenly have a different view in which you can look at it. Understand? Okay. So the next one is next architecture is the convolutional neural network. So as the name suggests, it basically uses something called convolutions. It's a little more technical, like than AutoEncoders. AutoEncoders are they pretty much look like a regular fast forward, feed forward method, right? The difference here is basically, and again, I'm not an expert on CNNs, so if I'm wrong, please correct me. But they are mathematical operations which make it interesting, right? It's called convolutions and pooling, basically, the subsample, right? So if you look at the picture here, so let me draw your attention to these tubes which are going, like these three-dimensional tubes, or which are going from, say, one layer to the other, right? So what it really says is that when you push your data through each of these layers, right, the next layer may or may not be using all the data available at the previous layer. Okay, so it is basically learning some sort of representation at this layer, and some part of it only is useful for the next layer. And that is sort of convolution. I'm not going into the mathematical definition and all that. There is a lot of literature which goes into this. But in the idea basically is that you're learning certain representations, and then you basically take the knowledge from one layer, and you're pushing only a subset of that knowledge and pushing it to the next layer. Okay, and almost all, I think all convolutional neural networks have this architecture. You start with of course, your input, and then you have these convolution layers, and then there is a pooling operation. Pooling is a little different as well. So what you do is when you take the data, which is going from one layer to the other, you basically do a subsample. You take what you say the average, or say there are different operations. There is a max pooling operation, which basically says that I will take the maximum of all the data which is in that subsample, the small sample, and then I'm going to just push that to the next. So it's a little more technical, but this is what really these architectures really became very useful in, say, your video and your face recognition and video, right? So before I go to the next one, I would also like to give you a little, ask you a question basically. So what is the main difference between, let us say, a regular, when we do a time series prediction, or when we do a regular, classification task? What is the difference between, an image classification task versus a regular classification task?
What's the difference between
an image classification task and, let us say that I have a vector of data and I'm trying to do some other classification task?
learning the features?
Yes. What is the main difference? This is an image, right? What is the difference between image and any other regular classification you get? The data, right? Right? The data, the representation, it's two-dimensional, basically, right? You start with an image, you get. So you know how image data is represented, right? In pixels. So each pixel has a value, and then it's a matrix, right?
Usually it's three-dimensional.
Yeah, and when you add video, it becomes 4, right? And that is the reason why Google calls their framework TensorFlow. So, right? So, if you have heard about the word tensor, tensor is nothing but more than two-dimensional data. It's a representation, right? It's basically a matrix which has more dimensions. Okay? So, convolution basically looks at that. The next architecture which I'm going to talk to you about, it also does the same thing what CNN could do, but it adds another layer, right? It adds a time dimension. Okay, so image classification is great, right? But it's pretty much, again, if you're looking at static data, you're not looking at trends, you're not looking at what happened before that image happened, right? Or that particular sample, what you say, event happened, right? So we know that there are other types of predictive models which exist, like for example, time series analysis. So you're looking at trends, you're trying to predict, like you have, let us say that there is a variable which is changing in time, right? Like a stock market, for example, the stock index, right? The Dow Jones. And then you're trying to predict what's going to be the value of the Dow Jones index. Like I know that you're saying that. That's an example, right? And then you're trying to predict like what the value of Dow Jones is going to be at the end of the day, and then you're trying to follow along. So how can you do it with something like a deep learning? So the problem we saw in the previous one, and like even with AutoEncoder, was that there is no time component to it, right? Like you start with one example, you learn that example, you do that operation. Second example, learn the example, that operation. So there is no concept of what was the value of the same thing in previous times, right? So to answer that question, there was another architecture basically which was looking at sequences of data. It was not just looking at a static point in time, right? So that's what the RNNs do. So RNNs. Before I could get in here, there's a little gap in this presentation, as you can see. I haven't talked about activation functions, right? Or the actual units which happen in that unit. So the basic idea is this. So I said that there are all these nodes here, right, in the architecture, but I never talked about how these nodes work, right? So I'm not going to get into that again, but the idea is that those nodes make all the difference. Those nodes are actually basically they make the difference between like a CNN and an RNN or an LSTM or any other architecture. Okay, so if let us say that when you start with a regular CNN or any other feed-forward neural network, and you have one of the nodes which is A in this picture, right? The difference between a recurrent neural network and the previous regular neural network is that there is basically a feedback loop between two time steps here. So what really is happening is that you can feed this network a sequence of data. So for example, you can feed it a video, which is basically a frame, which is like n frames one after the other, right? And this will learn from that. You understand? And if you don't want to talk about images, the idea basically is you can basically give it a time series, right? All at the same time, and it's going to learn from the whole time series. Okay. By the way, in the talk, I also have included a lot of references and links. So if anything is not very clear and all that, there are so many really good blogs and references there, which you can go through and try to learn from there as well. The idea basically is if you really want to go deeper into say different neural networks, you cannot just learn from one slide, right? You need to learn from a better source. Okay. So, and this is my last slide for the architecture. Sorry to bore you guys with this stuff, but this is kind of important. Then we go to the next, a little more interesting part. So, LSTM is a variant. It's basically it's an improvement over what we call as a recurrent neural network. And I'll give you a little bit of background why even we needed an improvement, right? So the problem with recurrent neural networks are basically a plain feedback loop. You have a small change. The idea basically what really happens there is that you do the back propagation, you read from the event or the data at that point in time. But you also learn from the one which is after that or after that and after. Right? You can go back in time as long as possible, as long as you can provide data, right? The problem is that when you do backpropagation on these different time steps, an issue happens. It's called the problem of vanishing gradients. So, how many of you have heard of stochastic gradient descent or gradient descent, right? So, that's how basically we we do optimization of certain functions in in machine learning. But the idea basically of backpropagation is that when you push an example through the network and you come at the end and you predict a value, it is not going to be the value which is supposed to be, right? It's a supervised algorithm, right? So you have you basically say y equals f of x, and you try to predict a y hat, which is a different number, and there will be an error, right? So backpropagation basically is the process through which you take that error and you propagate it back through the units or through the layers in the internet. So that's how it learns, right? So basically, it basically says, oh yeah, this is what I've learned today, and this is the value of y hat. But there is an error, so obviously I'm not very good at it, right? So what it does is it takes that value of the error and propagates it back into the network, and it basically there are weights in the network at every node and all that, and basically tries to adjust those weights, and it keeps doing that until all the it has gone through all the examples, right? And the idea basically is that the overall error for all the examples is the weights. So just like any other machine learning algorithm, a little bit, right? So when you do the same thing, not with just one value, but say n values in time, you have to basically do the backpropagation in time. You have to go back, right? And the problem, to put it simply, what the vanishing gradient problem is that as you go back further and further in time, the gradient of the error or the fitness function, right? It becomes very small. So the amount of adjustment, right, that can go into those units, it becomes smaller and smaller because it's proportional. Okay, so what actually happens is that as you go further away, let us say that you have a time series which is worth 2 years and 5 minutes apart. So you have every 5 minutes you have data, and it's worth 2 years, right? And you want to learn all 2 years of data. What really might happen is that for 6 months, going back in time for 6 months, it may not learn anymore from the previous year, right? Because of this problem. So to counter that problem, and there is also another, the opposite of that problem to solve the exploding. So sometimes what happens is your gradients actually can start accruing and they become really large, and that's also a very that's something which you don't do. So LSTM is basically a variant where you saw what that small feedback loop was between those two numbers, right? The previous. So this is your unit at time t-1. This is your unit at time t+1, and there is some feedback that is happening in between, right? It's learning from the the value in the previous time step. So LSTM basically does the same thing, but there is a different architecture here. There are some gates and all. It's very technical at this point. In any case, I would really recommend you guys to learn from the first. It's actually a blog from Mika Kola. Have you heard of this guy? He's a great engineer actually, and he really explains what is happening inside an LSTM unit. Okay, and how it actually deals with that problem of vanishing gradients. So in essence, what happens is, with LSTM, you can be rest assured that the vanishing gradient thing will not happen, and if you give it a sequence, however long the sequence is, it will learn from all the values. Okay, so to give you an example, especially in healthcare, let us say that I'm trying to predict a patient's history, medical history, what is going to happen to this guy in the next 6 months, what kind of procedures he might have to undergo, or what kind of diagnosis codes would be what do you say, I'm predicting basically what kind of diagnosis codes are going to happen to this guy, given that he has, say, 2 years of history, right? So I know when and what happened to the guy. I know exactly which day, what happened, like what diagnosis codes was formed or he was diagnosed with, right? And what procedures he went through and all that. So the idea with LSTM is that it can learn from all the 2 years of history, whereas the RNN may have an issue with the vanishing gradient. So it might basically cut off after, say, 6 months, and it may not be able to learn anything after that. And it might be useful. It might, depending on what use case you're working on, it might be important to know all the history of the guy, right? So, for example, if somebody has he was diagnosed with cancer like 6 months ago, right? There is a very little chance that that guy came out of it, right? So you should be able to predict that after a year period. Understand? Like it's a chronic condition, right? So stuff like that. So LSTMs are better at learning that. Okay. The best part is that because these can these data sets, they can take any sort of tensor or any dimensional data. Right? They're also very good at learning from videos. Right? Have you seen how crazy it is? Like I saw an example of a friend of mine was sharing. Somebody replaced Harrison Ford's face in every frame of the Indiana Jones movie with Nicolas Cage. That was not funny. It killed the movie for me. I'm like, my God, what? Right? And so it can learn that. It can learn it from. It can also create programmatically in Nicolas Cage's face, and it recognizes wherever Harrison Ford is and it's replacing it. Right? So, and that's an LSTM. Okay. So it's very powerful. It's a very it's complex, reasonably complex, but it's very powerful. Okay. Any questions, any guys? Anybody? So far? No. Okay. Let's get into some a little more interesting, right? I think this is what is more interesting because we want to see some examples of how these things can happen, right? About what you can actually use these. So I told you guys that AutoEncoders are useful, and I'm going to give you an example how it is useful. Okay. So for this case study, what I'm trying to the point I'm trying to make here is that using an autoencoder, I will show you that I can improve the performance of a regular classifier like a random forest. So we start with a classifier. We start with data set. I try to fit train a model, right? And you guys have already. So anybody who hasn't heard of an ROC curve or area under curve measure for classification, it's very common, right? The ROC curve, and then you get the area under the curve for performance, basically, right? So I'm going to show that the autoencoder, after using an autoencoder enhanced data set, I can basically improve the performance and area under the curve, basically for a random forest. Okay. So the data set I'm going to use is a prostate cancer data set. It's a tiny data set compared to what we basically use. It has only 380 rows. About 153 positives, so it's basically a classification data set. So we are talking about whether a person would have we are trying to predict if a person is going to have prostate cancer or not, right? And to basically fit that autoencoder model, I'm going to introduce another software which is video. Yes.
So what kind of features are?
Yeah, I'm going to talk about it. Next slide. So before we get into the features, I'm gonna introduce a little bit another software. So how many of you have actually heard of H2O? Right, and have you used it in workplace and all that? Yeah, it's pretty awesome, right? It's really good. It's an open source technology. It's inherently parallel, and it's based on Java, basically. But it has hooks to other programming languages too, like APIs, right? So you can basically fit a H2O-based model on top, like using an R interface. You can use that during the Python interface. I'm going to use R here. And it offers a lot of like general purpose models which we use day in, day out, like GLMs, GBM, random forest, and all that. It also offers its own deep learning package, which right now I think it has AutoEncoders and convolutional neural networks, and of course feed-forward neural networks. They are not. I don't think they have. They are offering RNNs or LSTMs as of now, but they're working on it. Okay, so the prostate cancer dataset has these features we're talking about. It has Gleason score. The Gleason score basically is like it's basically a score given to given by pathologists to people at different stages of prostate cancer, and I think it is an integer between 1 and 10, so it's an integer value, but basically changes between 1 and 10. The other feature I have is the PSA, or the prostate-specific antigen. As it says, like it's basically a protein produced by normal as well as malignant cells, and depending on what's the value, it's basically like a test which people do for prostate examination. And there are a bunch of other like features too, like DCAPs, DPROS, volume, which is the tumor volume, and the target variable here is called capsule, which basically is a binary variable and says whether tumor penetration happened for the prostatic capsule. I don't really know what it means.
Is that outside the prostate's gland, maybe the capsule is kind of like a layer of tissue around the gland. So has it penetrated outside the capsule of the tissue that's related?
And what is that supposed to do?
Higher risk of
having cancer.
Or harder to get to the prostate.
Okay, thank you. So guys who have experience with R, so this is how you can install a package called H2O before you start working on it. So just install that package with H2O, and then use library. You can call that library using library H2O, and the data set is actually available. Like it's pre-packaged with H2O's package. Okay, so you can just call it using these commands and read it into data frame inside out. So this is our visualization of all the different variables inside the data set, and I basically separated them by the target variable, so to see if there are any differences or any correlation between the target variable itself and and the different predictors we have, right? So you can see that some of them they don't look that different. Some of them they have some variation, right, between the two classes. So that gives you an idea of which predictors might be more useful in predicting this problem, doing the classification. But basically, this is something what you do, right? Initially, when you start preparing a model, you just want to have a deeper look inside your data and see how the data, different variables look like, and how distributions look like and stuff, so that you can do some sort of pre-processing or feature engineering if you may on top of that, right? So after that, what I do is basically to benchmark the problem. So I'm not going to do any feature engineering, nothing, right? I'm just going to fit a random forest model to whatever variables vectors I have to be able to predict the capsule penetration with it, right? This is a classification problem. So I use this code. I use the library random forest from R, right? And once I predict it, I can use a package called PROC. You guys have used that before? Part of PROC or ROCR. There are multiple packages you can use. So so all this code is available. So if you want to just if you haven't done this before, you just want to check it out and do that. And of course, there are similar packages in Python as well. I just decided not to use Python in this presentation. Just keep a uniform, just using R only. So once I do the training, and then I basically plot the ROC curve. The area under the curve, the AUC value for the random forest value model I got was 0.757. Okay, so that's one benchmark. That's basically saying that, okay, I use the random forest model with the bare bones like data what I had, and it's like the performance of it, right? Some sort of. So next time I do something, I can compare it with this value and say that, okay, if I got any better or if I got any worse, right? So H2O actually, as I said, like, it has its own like package, deep learning package, provides autoencoders, also CNN models. So I'm going to use the autoencoder model here. So in the so again, like because it's H2O, I'm going to attach the package H2O, and then you have to use like you have to basically initiate the H2O cluster. But it's all easy. You don't have to do anything special for that. And then what I'm doing is I'm taking the whole data set, the whole prostate cancer data set, of course without the target variable, right? And then I'm putting, I'm basically training a deep learning, an autoencoder model. The code is within the green box. Okay? So in this model, I don't have a pointer, but if you could see, I'm giving it in, I'm giving the feature names in and the training frame, the actual data set, and I say autoencoder equals true, so it knows what model to, like it's basically fitting an autoencoder model. And then the bottom, I'm actually defining, so that's like a one line, one statement, right, which defines the architecture. So what I'm saying is there is one hidden layer, right, and there is one input layer and one output layer. So the input layer has 6 nodes or 6 units, right? And the hidden layer has 5 units, and the output again has to be equal to the 6, which I'll come by, right? Remember, we start with like n dimensions, we end with the same number of dimensions. So, but what I'm doing is I'm reducing the dimensions by just 1. Okay, so we can play with like multiple. There are ways to like even what you say tune hyperparameters automatically, but not going in there. So in this case, I'm just saying, because I want to change it, I'm going to reduce the number of dimensions to 5. After that, in the red box, the code basically shows us 2 things. So the very first thing it does is that once you have already like created the model, this here I'm calculating what is the reconstruction error per sample. So I have the data set. And I created like a training, I trained that autoencoder model, but I said that autoencoder has error, right? So when you reconstruct, when you reduce the number of dimensions, so you're compressing the model, so obviously there is error. The idea basically is that when you take so many like samples, not all samples have like are easier to reconstruct, right? So the error might change depending on how difficult the sample is to reconstruct, or the sample is to even understand, right? So when we started with the initially with the random forest, I pushed all the data in there, and I basically said, oh, we have 0.757. It's not really that great. Like we would like to have a little more performance, but in this case, what I assumed, my principal assumption was that not all the samples which I'm trying to fit the random forest with, right, are equally are similarly like modelable. Like it's very difficult to learn some of those samples. The patterns might be different, a little bit different than some of those samples, right? So the idea is that the autoencoder is helping me do that, helping me understand which samples are difficult to learn from compared to some other samples. Does it make any sense to you guys? So inherently, what happens is like there are trends in the data, right, which makes certain samples to be difficult to learn from, especially using a random forest, right? Because another thing is that you don't want to learn exactly what is happening with each and every sample. That will be overtrained, right? So you want to have a model which is generalizable enough. At the same time, if there are specific patterns that are repeating in the data, then you would like to pick this up. By the way, autoencoders are used a lot, especially in the modern times, in anomaly detection. Okay, so you know how people, like especially in cybersecurity, or like if you have any time series-based anomalies, you have anomalies in, say, a supply chain, some event happening, then you're expecting, say, some amount of production in this production line and it did not happen. How do you figure that out, right? So, these are very rare events. They don't happen all the time, but when they happen, they can, trigger like a set of events which are not good for your overall process, right? So the idea is how you figure that out, right? So anomaly detection is one. Yeah, sorry.
So how would you train an autoencoder to pick something that's rare? Usually, my understanding of neural networks is that generally they require a decent number of training examples of each class.
Yes. So this is just a toy problem, but the idea basically to pick up this problem was that it actually still shows some some pattern which can be picked by an autoencoder, which is as simple as this.
But you'd still have to train it on a good number of classes or a good number of data samples that you call an anomaly.
It really depends, right? So I see. If I have a data set which is multidimensional, you're talking about like 100 million, say rows, and I have about 100,000 features, right? Then yes, then you need a lot of data and you need a bigger network. Here I have a very small problem, which is like I have only 6 variables. So this is basically like I'm trying to show that even here, it could pick up like a trend. You say that okay, if of course there is a right. So I'll show you in a moment like what I really mean by that. So in the red box here, what I'm trying to do is that I have already fit an autoencoder model, right? And then what I'm trying to do is I'm trying to calculate the reconstruction error per sample. So every sample, when I reconstructed using my autoencoder, it did not end up giving me the same amount of value, right? So each feature had certain errors. So if I add all that error or take a mean of all that error, I get the mean reconstruction. Or I can even do per feature error as well. So in this case, I'm looking at the mean error. So I have 6 features. I scale the error by the feature, and I take the mean of all those 6 different values, right? So if I take that error and I plot it here, the one on the top that shows you how the error looks like, and you see that for almost there's a trend almost to about 300 of those samples what I had, their reconstruction error looks pretty much okay, and then suddenly certain samples have a really high reconstruction. So what it really means is that my autoencoder model, it found it very difficult to reconstruct or learn and reproduce those samples compared to the others. Does that make sense?
Now, those are all the samples on the X coordinates, but how do you sort them?
Yeah, so I just sorted the values because here which sample is what doesn't matter, right?
But then it doesn't matter how you get them in first and put out to create the error in the first place?
Oh, no, it doesn't. So are you saying that if the order of the samples matter? No.
Yeah, because looking for a trend, let's say Gleason score, actually, that is probably the crux of the argument here. That is predictive of the target variable integration of the capsule.
Yeah,
higher Gleason score is equals higher risk of metastasis.
So higher reconstruction error is representative of the fact that it's difficult to reconstruct. That's it. Now, is that something which is structured or integral to the classification problem itself? I don't know. In the sense that here I'm not claiming that it's basically picking up, it's already showing me class 1 versus class 2. That's not happening. If that happens, it would have been a coincidence. By the way, and this is what really is happening here. So class 1 and this is not the same as a classification problem. What I did was to just show how it separated the values. I basically created another binary variable calling. So remember our target variable was capsule. So this is class. This is basically just a separation between, say, the reconstruction error at some arbitrary point. So in here, what I did was I basically said, okay, So if I take this line right here, right, it looks like a good cutoff, right? At 0.1, if you see. So if I take a cutoff here, these look like they're pretty well mannered. I can imagine that there is a very small trend, but they're pretty much like they're not like a order of magnitude high, something like that, right? But the reconstruction error for the other samples is comparatively pretty high.
I know you have some very interesting slides coming up.
Oh yeah, I think
just one, yeah,
yes.
to like jump around.
Okay, so basically, that's how I divide the data set now to to see if something interesting is happening, right? And the yellow bar here, the yellow box, basically, I wanted to show you what the hidden layer looks like, the representation. Remember, I was talking about it is basically like a PCA, nonlinear PCA. So you can extract the hidden layer, and these are the top 5 samples basically, and their representation in the so you can use them as, say, new features, for example. Okay. So what I did was basically I said, okay, now I'm going to separate my training data into samples which had reconstruction error less than some cutoff, and then into another sample which is greater than some, right? And then what I do is I fit a random forest count on top of that and see if it gets any better, right? So this is for the larger data set. The one with about 300. So the cutoff basically separates it between a sample which is about 300 rows and the other one is about only 80 rows, right? So this is the larger sample, and the AUC now for the random forest fit on that data, it got a better yield, right? It's at 0.78, it's about 3% yield, right, compared to the previous one. Okay. So okay, yeah, that means it. Now let's see if that is a trend, right? It might be a fluke. Sorry. So now I took the second data set, right? And then for the second data set, I did the exact same thing. And what I'm expecting is that if the whole data set had an AUC of 0.75, that was the average accuracy, right? And the accuracy increased for one of the data sets, it should decrease for the other, right? Because the average was at 0.75. That makes sense? Because the other data set is difficult to model, basically, using a random forest. And yeah, it looks like, because now it has come down from 0.757 to 0.75. Again, it will be a good question to say that, okay, there are not enough samples, but my model is not very complex. It's a very straightforward, a very shallow model. So, good. So far, what has happened, I have expected something and something similar has happened, right? So how do I try to use both these, observations and get to a better classifier, right? I bagged it. I created 2 models, right? So I can take the whole data set, push it through one model, whole data set, push it through the other model, right? And then I get predictions out of those, and then I take the average prediction. And then I can create an R seeker out of that too, and the AUC is much higher. And that is kind of expected, right? When you bag, even though so the whole point of ensemble learning is that you start with some weak classifiers, but when you combine the prediction for those weak classifiers, it's going to give you a better prediction, right? So that also is happening, but it's definitely a good, it's almost a 6-point yield, right? That's pretty good. Any questions? Yes.
So, how much data was in the outlier group?
About 80 points.
And then did you train a new model on each one?
Yes. So when I divided the 2 data sets, I basically ended up teaching a model for the first one and then training another model on another one. And then I backed those 2 models to show what happened at the end. I think.
Yeah, and any questions from the floor? We are almost time, and then if you have any questions, if you have any feedback, and you have any brainstorming idea for Aaron, and you can check out our meetup site, and then we can talk over there. And I think you will post your PowerPoint today, right?
Yes, I'm going to post my PowerPoint.
Okay.
So before I finish, what I'm going to do is I'm going to run through the slides and just tell them what it is so that they understand what
Sure. Yeah.
Okay, so the second case study is basically a model which uses CNN, and the reason for that is that it's basically like a classification model for peptides. It's basically like a cancer immunotherapy model. There is a lot of literature around it, which I've posted links for. But the idea basically was that it's not an image. So what we are really looking here is the data. I'll show you one snapshot of the data. So this is like one case which goes into the learning model on a convolutional neural network, and I represented it as a picture, right? So in the picture, it is a 20 over 9 matrix, right? And each pixel in the matrix is actually a probability. So this is actually a transition matrix. Okay, so these kind of things happen. It doesn't have to be an image, but because the input data is two-dimensional, convolutional neural network helps really well. And I do exactly the same thing. I show basically a comparison between a random forest model, which was like run on the same data, and a convolutional neural network, and how much yield it got out of. By the way, this is a very famous example. This is not my example, obviously. So I have references for all of these in the slides, and also at the end of the slide in the references. So please take a look at it. And by the way, this model, this uses Keras inside of RStudio. Okay, so Keras is basically, it's a Python package, right? Python framework. People use Keras to, fit deep learning models, but you can do it inside R. You have basically you're writing R code. You don't have to run Python or the specific semantics, right? Like for Keras. But you can still fit a Keras model. Of course, you need to have Keras and Python installed on your computer. Okay, so because it needs those packages behind the scenes, but to actually program and run around, play around with it and all that, you don't need it. And the next example basically was about word embeddings I was talking about, right? So it's very interesting. So how many of you have Amazon Alexa or a Google Assistant or speaker something at home? You know how conversational they are getting, right, day by day? We talk to them, we ask a question, it pretty much knows what it's talking. I cannot talk for Alexa. I'm really mad at Alexa because it doesn't understand my accent, but but it still does a good job. It still runs all the lights at home and everything, right? And so I want to draw your attention to the fact that when Alexa started, right, you needed to frame your question in a very specific way, right? If you don't, if you do not follow the pattern exactly with only some changes you can make, it doesn't even know what to do, right? And then Google Assistant came, and Alexa also improved a lot. Now you can converse with it. All it needs is keywords, some keywords in there, and it knows how to go back and understand your question, right? And one of the major technological advances that had happened was word embeddings. The idea behind word embeddings is that if you take a huge amount of text, right, which basically say are part of a journal. So there is a context to the journal, right? So have you heard of LDA or topic modeling before? If you have done NLP, right? So you know how LDA is looking at context, and then it's creating these joint probabilities and whatnot, right? So what word embeddings really does is that instead of throwing some sort of topic at you, a randomized topic at you, what it does is it represents your words inside not a linear but a vector space. Okay, so what it really does is it assigns coordinates to each word. Now, is it static? No, it really depends on the context of the document it was learning from. So if you throw journals at it, it understands the language inside the journal, and then the vectors it comes out with, it tells you how close those words are in that vector space, which is very useful. So one of the examples here is that if you can, say for example, put your words in a male-female dimension, whether one dimension basically says if they're all male words, and the other dimension has female words, you can basically create like a distance vector or a distance measure between, say, king and queen and man and woman. So it understands. If you say, so let us say, and these examples are all over the place. If you ask a question, okay, what is a queen to a king? Oh, sorry, what is a man to a woman? What a king is to a what, right? And it basically comes up with the answer queen, because that is the closest thing in those dimensions. So it understands the context as well. So the context was male-female dimensions, right? When you started with the example man. So that is how it goes. So it's really useful, right? And it doesn't have to be general conversational stuff. So the other example, basically, so of course, there are all sorts of like architectures for this, but the one I was interested in explaining was the word2vec, which is basically a shallow neural network. It's actually a neural network which is those networks. And it's one, you teach it only one time, so you don't have to break it again. Unless the context changes or something else happens with it, right? So it creates like a full representation of the vector space, and also the dimension of the vector space. And by the way, you can start with, say, for example, 10,000 words. That's like usual, right? If you have a document. But you don't have to have 10,000 dimensions. You can actually compress the whole thing into, say, 200 dimensions, 300 dimensions, and just okay. And for people who are interested in healthcare, there is a world embedding example which is already there, created by Georgia Tech with the Children's Healthcare of Atlanta. And they call it Med2Vec. It is actually pretty awesome. We have been using it in all the examples we have been working on. And what they have done is they have basically created a word embedding for regular healthcare terms, like CPD codes, ICD-9 codes, and what's the third one? Yeah, not DRGs. I think HCCs are there, and then they also have a second layer added to it, which looks at visits. So what they're doing, the context is not just like medically relevant terms, but it also takes care of, like, if you have data from one visit and then you make another visit, it looks at the temporal aspect as well. How close the visits were is important. So it's actually pretty good. Yes. Is
that kind of like a jar file or anything?
Yeah, so it's not a jar file, it's not an executable. So see, this is the beauty about it. You don't have to teach that model again. All you have to do is if you download the embedding itself, it's basically like a lookup table, and it is good to go. So they have the lookup table like in their website in the references, so you can check it out as well. I have put in the references for that. So
you stick it in the table somewhere.
Yes, and then all you do is look it up, like and the idea basically is that all words are vectorized, so you can have like a weighted vector for your whole document, and you can use that in, say, a regular. So yeah, so this is what people have been up to, right? All the NLP methods, what we have been doing so far. They don't give you a direct way of creating features on it, right? So this is like basically directly creating numerical features that you can use in other models. Thank you so much, guys. I think that's all what I had. That was another example. It was a nice shiny app. You can play around with it a little bit. It basically learns from speeches and then generates speeches which sound like President Trump. So it's kind of funny, and it's a nice way. Yeah, it's basically like text generation. So it reads from all the Trump speeches in the past and learns a model, and then if you ask it to produce words like 200-word passage or something, the style is very consistent. You can see that. Yeah, the style is pretty consistent. It loves that. So. And it's a shiny app, so it has a interactive visualization. Thank you so much, guys. Any before we leave, any questions, anything, please let me know, and we can talk after this. And thanks for bearing with me.
And so if you have any questions for Aaron, and if you have any idea, and then if you have any idea that you want to share with us, let us know. So next time we take a look here.